Now it's time to make a little conclusion on all the notions we discovered or rediscovered in today's videos. I recognize that it's a lot of information and it might be hard to keep up. So in this conclusion, I'll try to consolidate everything we learned and how to use it as efficiently as possible. We learned that casts originated from one particular cast action, the conversion. The conversion was what would allow us to transform the bits from one value after the coding of another value, of another type. In order to convert this value efficiently, remember the integers, floats, and doubles. The representation. The way these types were coded was different. Therefore, to go from one type to the other, we need to convert these values. We also saw that there are a particular type of conversion, the identity conversion. Bits after conversion were not reordered. We had exactly the same bits in the order. This particular type of identity conversion was called a reinterpretation. Then we saw that reinterpretations would allow us to work on more generic, more accurate types of addresses, and have something interesting, and that there were particular types of reinterpretations. They are the upcast and the downcast, which will allow us to navigate through a vertical class hierarchy. And we also saw that it was possible to reinterpret a type using the type qualifier and add the const keyword. It would also work with the volatile keyword, but it was less interesting here. So all these cast actions were something you would feel intuitively, but I hope that after these videos you have a good idea of the related vocabulary and semantics. We also learned that C++ offers 5 casts, including the implicit ones, as opposed to the 2 in C. We had the implicit cast, the static cast, the dynamic cast, the reinterpret cast, and the const cast. We also had a good old C cast, which we will never use again in C++, but it's still present just for legacy reasons. To better understand which cast can do which cast action, let's study together a little table summarizing all this, so we can get an understanding of this. Of course, I encourage you to check this table for reference in the future when you need to clarify your ideas. Here we have a first little table in which you and I have in columns the different cast actions at our disposal, namely the conversion, the reinterpretation, the upcast, the downcast, or the type qualifier reinterpretation. Here in the rows, the different casts including the implicit cast, the static cast, the const cast, and the reinterpret cast. I also added for you information and for comparison purposes the old legacy C cast, till we can see that the C cast is a little bit too permissive. Let's start with it. We can see that the C cast is able to make conversions, reinterpretations, upcast, downcast, and type qualifier reinterpretations. The problem is we don't know which one of these cast actions the C cast will perform in C++ context. It can be any of them. Adding a little bit of randomness in C++ programming is definitely something we want to avoid as much as possible. That's why from now on, you'll never use the C cast in your C++ programs. It will be a reason for point loss. However, you must become an expert on which C++ cast to use in which conditions, and in more particularity, which advantages these casts will offer. The available cast actions for implicit casts are conversions and upcasts. We learned this through different examples. I don't remember having said this explicitly, but we can see in this summary that the implicit cast has worked in the conversion and upcast context only. Then we have the first C++ cast we learned, the static cast. The static cast can be used in 2 different environments, the conversion of simple values, and also in the case of upcast and downcast, in which we have a full understanding of the inheritance tree. We know what we want, we know where we're going. In this context, we'll use a static cast. We also saw the static cast would allow a certain number of checks, but would keep some flaws. Remember that in an inheritance tree, if we had a type being the left branch, and we static cast a base of the left branch type to the right branch, the static cast wouldn't prevent this cast. However, we would have some trouble at runtime. Nonetheless, we saw the static cast would prevent casts between classes from different inheritance trees, meaning that we have a horizontal hierarchy this time. The static cast would stop us from doing these casts, since that kind of thing should never happen. There is no concrete actual example in which we could want this type of cast. Then we have a dynamic cast, which was a very particular type, because it was the only one happening at runtime. It's not made at the compilation, but when the code is run, the dynamic cast adds a certain number of performance overheads to your program, since it takes advantage of what is called the C++ runtime information, the RTTI. To enable the RTTI in C++, the class must have at least one method, meaning a virtual member function. Once all these conditions are met, we could use the dynamic cast, which advantage was to check if the transfer from one floor of the class hierarchy to another was realistic, which means that it fills the lack we had with the static cast. If I want to downcast from a mother class to a daughter class without knowing if the actual type of my mother class is the one of my daughter class using the dynamic cast, I'd be able to run this test at runtime. By the way, I explained to you that it was one of these base principles, hidden behind the notion of plug-in. Very interesting. The dynamic cast is a cast you will encounter quite often. Here, I inverted them, but that's okay. Let's talk about the const cast. We saw that it was the only C++ cast allowing to make type qualifier reinterpretations. This is a cast you will use very, very little, and the rare cases in which you will have to use a const cast will be design flaws. You either edit the code if you can access it, or make a const cast to be able to keep coding since it's not your fault. Then comes the reinterpret cast. We saw that it was the most open cast, which would allow to make reinterpretations. Upcast and downcast, but without any semantics checked this time, meaning that you can make an elephant fit in a mouse with the consequences you can imagine. One of the most common and relevant uses of the reinterpret cast is the case in which you want to change the type of some raw data. I told you about data coming from a socket or something like that. Or you want to program the type of this data to a type usable by your program. In this case, reinterpret cast is the way to go. I have a second table here, which will give us a bit more information about what the different casts are able to do. I mean, do these casts have any semantics check? I summarized it here, but we'll see that some do, some don't. Is the cast performed at runtime? I mean, once the program is compiled, does it imply that the program will run fine? Sometimes it does, sometimes it doesn't. And is the cast performed at runtime? So here, the only case is the one with the dynamic cast, then the implicit cast, the static cast, and the dynamic cast do have semantics checks, as we saw in the different videos, which is not the case with the const cast or the reinterpret cast. By the way, we can see the legacy C cast has no semantics checks. It's open bar. You can easily blow up your program, so you should never use the C cast again. Then, as we saw, once a program is cast, is it reliable at runtime? In the cast of the implicit cast, since we only had conversions and upcasts, the conversions were raising conversions as well. Then our program would be reliable. There's no risk of it blowing up. However, there is no test performed at runtime. With implicit cast, this isn't a big deal. We saw that for the static cast, we have a number of semantics checks performed, more particularly to ensure that both types belong to the same class hierarchy and aren't detached. However, this doesn't mean that our cast is reliable at runtime. Remember, when I do a static cast from one branch of my inheritance tree to the other, it will be compiled, but we would have catastrophes at runtime, and the static cast is definitely not tested at runtime, as the name static cast implies. Static made during the compilation, dynamic made at runtime. The dynamic cast now, we definitely have semantics checks. That's what will allow us to make sure that we are in a suitable inheritance branch. Is it reliable at runtime? Yes, since it will be tested at runtime. we'll be able to check it in a situation in which it works, and in a situation in which it doesn't. An error is properly generated, which you can manipulate to inform the user. In short, your program doesn't blow up miserably. You keep control. We saw that constcast and reinterpretcast had no semantics checks, weren't reliable at runtime, and weren't tested at runtime, and therefore should be used with discernment and intelligence. That's it. I know it's a lot to remember. C++ casts are a complex notion. I think that's even one of the most complex you'll encounter in this Piscine. Take your time to be comfortable with all this. I recommend you do your research on the net to get more versions and explanations on top of the ones I gave you. Maybe you'll understand better it's explained differently. Anyway, that's something that should quickly become part of your C++ arsenal, since you'll be using casts very often with complex class hierarchies, programs using modules, a whole lot more advanced programming than what you did in C. You will quickly face cast issues, so get familiar with this. Get to know how to choose the good cast based on the context. Be smart. Take advantage of this Piscine day to get familiar with this. But don't worry, I know it's quite complicated and will take some time. The earlier you get to it, the earlier you will master this. That's the end of this interesting video session on C++ casts. I hope you enjoyed it and learned a lot. And I'll see you next time for a new video series. Goodbye.